Good afternoon. I want to continue talking about formalism, and today, first I want to introduce so-called determinate states, and then I will also talk about Hermitian operators, their eigenfunctions, and some of the nice properties they enable us. Let me first start with determinate states. So first let me remind you what we already know from the infinite well potential. So infinite well. So we solved Schrödinger time-independent Schrödinger equation, and we found psi n of x is equal to En psi n of x. And then we said if we calculate the energy, like let's calculate energy on these states, psi n of h, psi n, right? This is h times psi n is En, so this piece is En, and this En is a number, it comes out, and psi n is, okay, let me write in two steps, En, psi n, and this is En, right? We did it in the integral representation, but now we know the Dirac notation, we can make it a little bit quicker. We also considered square of this. Suppose I calculate not h but h squared, but that's no problem because h is h times h. Every time I act with h, I'm going to get an e, and the same thing is going to be En squared. And from here, if I calculate the variance of h on these states, sigma of h is defined as h squared minus expectation value of h squared, and this is En squared, this is En squared, so this is 0. So what this means is, if we calculate the expectation value of Hamiltonian in the energy eigenbasis, the variance of energy is 0. And you should compare this with like an arbitrary state, right? In the case of an arbitrary state, psi, let me call it x comma 0. So we need to expand this in the energy eigenbasis with some Cn, psi n coefficients, right? Now if I calculate the expectation value here, so h, I am going to find, right? Maybe I can assign this like a exercise because this is like really simple. What you are going to find is Cn squared En, right? And similarly, if you calculate h squared, so this is h squared, you are going to put e squared here. Okay, show this, okay? This is like awfully simple, especially with using Dirac notation. You can do it in less than a minute. So this is exercise. Therefore, in this arbitrary state, sigma of h is not 0. Good. So now I want to consider an arbitrary operator, and I want to ask the question, when do I have 0 variance if I calculate the expectation values? So let this arbitrary operator be Q. And from last time we know if this is an observable, this has to be Hermitian, right? And it has to have like real eigenvalues. So let's calculate variance, sigma of Q is going to be equal to, this is expectation value in some states, which you are going to find in a little bit, Q minus expectation value of Q. If you want, I can put heads. Maybe I can do the notation a little bit lighter by defining this little q. Then the variance is defined as expectation value of this square, right? But what is this? This means find some psi, put this guy, and so this is like an operator act with this operator on psi and take inner product with bra psi. And since Q is Hermitian, right, this Q hat is Hermitian and Q is real, I can rearrange this in a form. I can carry one of the powers to here, so this is going to be Q minus Q psi, and the other one is still here. This is Q minus Q psi. And what am I looking for? I am looking for a condition for this to be zero. I'm asking, when do I get zero variance? This is what I define to be determinate state. So if I set this to zero, I immediately find Q minus Q acting on psi should be zero. But what this means is like Q hat times psi is equal to Q times psi. This is what we call eigenvalue equation, right? This psi here is what we call eigenfunction. This Q, what we call eigenvalue. And if psi is defined with such a equation, we say that variance of Q on this psi is zero. So let me also write that. States with zero variance, and that's the definition of what I call determinate. Are eigenfunctions, or if you want, you can also call it eigenkets, right? Eigenfunctions of Q. So if this condition is satisfied, and if you measure what Q is on this basis, we get Q 100%. So let me write it. Measurement of Q on psi gives Q 100%. So this is just for one eigenvalue, but we can have a collection of eigenvalues for an operator, right? So the collection of eigenvals of Q is called spectrum. And another terminology is like, suppose I have one state, like psi 1 is equal to Q1 psi 1, and I have another one, psi 2, Q1 psi 2, and if I have Q1, okay, let me write it separately. If Q1 is equal to Q2, but these two states are different, let me write it like this: psi 1 not equal to psi 2, we call it spectrum is degenerate. So this is degenerate. Degenerate spectrum. So that's the keyword. So we introduce several things: determinate and eigenvalue equation. And we said that if we are measuring an operator in its own eigenbasis, it's going to be the determinate state. Let me give you an example. Let's consider Q to be I d phi, derivative with respect to phi, and this phi I define in 0 to 2 pi. Okay? If you want, I define an angle variable, and I define the derivative with respect to this angle. And I need to define also some boundary conditions on this, right? So in this space, sometimes people call it manifold, if you want to be fancy. It's, for us, manifold is a space, we don't care. And the condition on functions is f of phi is equal to f of phi plus 2 pi. Let me show this operator is Hermitian. So first, let me calculate on any functions f q g is equal to d phi from 0 to 2 pi f star of phi I d d phi g of phi. This is going to be, I am going to do by parts again, right? This is going to be I f of phi star g of phi from 0 to 2 pi minus d phi. Now I take the derivative here, I d d phi f star of phi g of phi. So I claim this thing is 0. Why? Exactly, boundary conditions, right? If you do 2 pi rotation, you come back to yourself and they cancel. And this one, I write this as, let me write it in 2 steps. First, I want to take this out and write like this. But I need to introduce an extra minus. Rather than introducing an extra minus, I erase this one. And from here, I see this is Q dagger, which is exactly what Q is, right? Then Q dagger is equal to Q. That means Q is Hermitian. In case you had doubts, yes?
Why did we raise the minus?
Because, so I did it in 2 steps. Let me take it back. There was like a minus here. So parenthesis was not there. So there's like this, and there's like a minus here, right? So 1 minus, sorry, it was like this. I just, let me copy in 2 steps. Erase this one too. So this time I didn't do anything, right? So what I do is I want to put this conjugation on this on entire object, because this is our definition of bracket, right? If I want to do that, I can do that like this. But there's like I, so there has to be a minus here. But like this minus, I can carry it out and cancel these two. Then I have this Q acting on F, G, consistently with our bracket notation. And when I look at the operator, this is I d d phi, and Q is I d d phi. From there I deduced Q dagger is equal to Q. Good. Now let's think about the eigenvalues. So Q acting on F phi should give us some Q times F phi. And our goal is to find, right, eigenvalue equation is asking for both eigenvalues Q and eigenfunctions F. We need to find these two, which is very simple because this is a first order differential equation. So this is I d d phi F is equal to Q F. And you can take d phi to here and put F here. And this is log, right? Log F is going to be minus I phi plus a constant. Also there's Q, minus I Q phi. plus a constant. From there we find f of phi is equal to sum a times e to the minus I q phi. So I found the eigenfunctions. To find the eigenvalues, I use the boundary condition. So use periodic boundary conditions. F of phi is equal to f of phi plus 2 pi. That means a times e to the minus I q phi should be equal to a times e to the minus I q phi plus 2 pi. And for this equation to be valid, I require q 2 pi should be some integer times 2 pi, or another way of saying that is q should be some integer, right? It can be 0, plus minus 1, plus minus 2, dot dot dot. And as an exercise, you can also try to normalize, to find f of phi. Now we can put q if you want to label the eigenvalues, is equal to 1 over 2 pi e to the minus I q phi, and q is given with this condition. Therefore here spectrum is non-degenerate. So as an exercise, you can consider q is equal to d squared d phi squared, exactly the same manifold, the same space, the same boundary conditions, and find the spectrum and see if it's degenerate or not. So degenerate we introduced here, right? We say, so if we have like two, like this, if we have two eigenfunctions, psi1 and psi2, and they have eigenvalues q1 and q2, if q1 and q2 are equal, whereas psi1 and psi2 are distinct, we call it degenerate. That's the definition. So if two different eigenfunctions have the same eigenvalue, that's degeneracy. Yes? How did we say? So here, here you can see, like eigenfunctions are labeled, so you are asking for this problem, right? So for this problem, eigenfunctions are labeled by q, and each different q has like a different eigenvalue, right? 0, right? They have one-to-one mapping. So the equation is here. So each different q has like a different eigenfunction, like this, and different eigenvalue. And to see the difference, you need to, for example, you can consider this thing, and it'll tell you the difference. So now I want to talk about like these eigenfunctions of Hermitian operators a little bit more. So you can see observables are Hermitian operators, and their eigenvalues seems like playing an important role. So we can like generalize some rules. Let's consider eigenfunctions of Hermitian ops. So the kind of things I am keeping in mind to generalize these things, like first, let me write this. Observables are represented with Hermitian operators. And now we can have cases, right? We can have discrete spectrum, and these guys are going to be normalizable. And you can, for example, think about infinite valve. Or we can think about continuous spectrum. in this case, as we know, they are like non-normalizable. But we are going to come up with a kind of normalization with like based on consent. You will see what I mean. But in some problems, we can have both continuous plus discrete spectrum. And for this, you can think about finite valve. Good. First, let me prove the most important thing. So, eigenvalues of Hermitian operators are real. Real in the sense they don't have any complex part. They don't have imaginary I in them. So if Q times F is equal to Q times F, then we require Q to be real if Q is an observable or if Q is Hermitian operator. So let's prove this. Proof. So let's think about this Q F is equal to Q F. So this is the eigenvalue equation. And I can take the Hermitian conjugate, take Hermitian conjugate of both sides. Then I'm going to have, as you know, I can absorb this Q inside F, and Hermitian conjugate, I can write it like this. Q F is equal to, if I take Hermitian conjugate, this is going to be Q star, and this is going to be F. And the goal is to show that this Q star is equal to Q. Then Q is real. Now, let's take F, Q, F. We know this piece is Q times F. And this is equal to, I can take this Q to other sides, right? Normally it's like Q dagger, but we know this is like a Hermitian operator, so Q dagger is going to be Q times F, and this is F. And I know this piece from this equation is Q star F. Therefore, this side is Q F F, and this side is Q star F F. If you want, you can from here we know F is non-zero. We are looking for like non-trivial solutions. From here we find Q is equal to Q star. Therefore, Q is real. Second important property, eigenfunctions of Hermitian operators with different eigenvalues are orthogonal. Let's also see, this is also kind of easy to see. Let's prove. Let's say I have Q F1 is equal to Q1 F1, and a second one is Q F2 is equal to Q2 F2. And I want to look at this thing. F1 Q F2. So this thing we know is Q2 F2 from this equation. And I can write this as like, I can carry this here, right? And this is Q F1 F2. But now I know this piece is Q1 f1. And I know q1 and q2 are real because we just proved it. And from here, what I see is q2 f1 f2 is equal to q1 f1 f2. Now let's collect q1 minus q2 times f1 f2 is equal to 0, right? I just combined everything in one side. Then if q1 is not equal to q2, that means f1 f2 is 0. And that means they are orthogonal, right? That's the proof. Therefore, f1 is orthogonal to f2. Yes?
How do we know Q1 and Q2 are different numbers?
That's what I assume, right? The proof, like this if you want, this theorem says eigenfunctions of Hermitian operators with different eigenvalues. So this is saying assume eigenvalues are different, we assumed, and show eigenfunctions are orthogonal. That's the job, okay? So there is also a third one. So eigenfunctions of observable operators, or like Hermitian operators, are complete. So that means if I have q fi is equal to some qi fi for a set of fi's, for some set, then any function f can be written as f is equal to some expansion in here c fi. And now, right, the expansion coefficients are trivial. We know ci is going to be some fi f. So this, unfortunately, there is no proof. I mean, there are actually proofs in some mathematics books, but if Griffiths is not proving it, I'm not proving it. Right? But from experience, we know this is the case, right? For the particle in a box problem, we know that's true because of Dirichlet's theorem, right? Any function can be expanded in terms of sines and cosines, and this is proven by mathematicians. We didn't prove it, but we know it and we use it. So consider normalization. 1 is equal to dx psi star of x psi of x minus infinity to plus infinity, right? And we can expand this psi. So this is saying that probability is right 1, right? Because psi star psi is a probability, and if you integrate over all possibilities, you need to have 100%. And now I want to expand this psi I. Let me use the same notation, ci fi of x. Now I am putting the argument x because it is going to be important. Then 1 I'm going to insert here, minus infinity to plus infinity dx, sum over all I, ci star fi of x. So I take bra to ket to bra, and the second one, so this object is psi star, and now I'm going to write psi exactly the same way. So this is, let me call it j, cj, fj of x, and you can see, so this thing and this thing, fi, fj, what is that? I think that's delta ij, right? Our beloved object. And from here I see sum over all I. There was like one summation for I. Okay, let me also do a little bit. So this thing, and this thing is going to be, if you want, let me be a little bit more correct. So this thing is delta ij, because I put the arguments. From here I have, and this delta ij is going to kill one of the summations. From here I have ci squared is equal to 1. Right? So all expansion coefficients add up to 1. That's what it is saying. But now I want to do a little bit something different. So what was the expansion coefficient? Let's run the calculation backwards to get like a different result. So the expansion coefficient was this dx, this basis function fi star, and this is the original function, right? This is how we find the expansion coefficient. And I can also write ci star, and I want to write it with like a different integral variable because these are different integrals, minus infinity to plus infinity. So this is di and this is dy, and I want to plug this in back here. Okay, so I already did the calculation, but now I'm going backwards kind of, but you'll see it's going to give like a different result. So that means I can do this. So this is sum over all I. If you want I, all possible indices. And I want to put this guy times this guy. Good. Now I look at this, and there's like summation over I, and the only I dependent things are here. So there's this guy, and this guy, and I want to bring them together, and then this will be dx minus infinity to plus infinity, dy minus infinity to plus infinity. I think one of them is psi star, right? So this, I wrote the complex conjugation here, but I forgot to write it here, and this one. So this one is star. I think this one is not, right? Yeah, I think it's good now. So this is psi y star, psi of x, and this is sum over all I, f I star of x, f I of y. And what was this equal to? This is equal to sum over all ci squares, and we know this is equal to 1. But I look at this equation, and for this equation to make sense, I claim this thing is delta x minus y. How? If I put delta x minus y, I kill one of the integrals, and there's only one integral, dx, and x and y becomes equal. This is becoming psi squared, and psi squared is 1. And from here I deduce this thing. I, fi star of x, f I of y. You see, previously we had I and j, different indices, but now we are fixing the indices, but changing the argument of the function. And this gives us delta x minus y. Okay? And in some books, this is called the completeness relation. Okay? Completeness. Maybe as an exercise, like consider particle in a box, and there, if you remember f, let me use fn of x. There was something like this: 2 over a sine n pi over a x. And from here, there's this nice identity, and prove this thing. N minus infinity to plus infinity sine n pi x sine n pi y is equal to delta of x minus y. Good. So you just need to do like rearranging of the summation index, and there will be like a delta function coming in, and you need to use some properties of delta function, but otherwise it's like a two-line exercise. Let's consider eigenfunctions of first momentum, and maybe later we can also think about position. First, I need to note, when we have continuous spectra, right? Now we don't have discrete labels. We know the functions we have to work with are non-normalizable. So, and we have to find a way to make sense of things when we cannot normalize functions, right? So that's what Griffiths call suburbs of Hilbert space. They are not entirely in the Hilbert space, but with some consistent treatment, you can use them as if they are in the Hilbert space. So let me start with momentum and then see how it works out. Consider momentum, like P operator is minus I h bar d dx, and we are considering x from minus infinity to plus infinity. This is our space. And we want to find eigenfunctions, and the definition of the equation, like eigenvalue equation, is P times f of x should give, if you want, I can write lambda here, right? But typically people use the same label, right? Operator is P, eigenvalue is also P, but you can see here whether I put head or not makes a difference. So I will not put a head, that means this is a number. I'll put a head, this means an operator. Okay? I mean, you know, you can use other letters if that's what you like doing. So this is f of x. And since we already showed P is Hermitian operator, we proved it for discrete case, but we also assume, like we are going to assume P eigenvalue to be real. Okay? Here, unlike the previous lecture, we have to assume it. Okay? And you'll see why. And what is this? This is minus I h bar d dx f of x. And this is a number, this is a f, right? First order differential equation is easiest to solve. Let me just write the solution. F of x is equal to some constant times e to the I over h bar p x. Okay? And generally, it's like a good exercise to label the eigenfunction with the eigenvalue so that you know. Like, and here we can put P as a label. Just like the index I we used in the previous lecture, P, which is continuous, is the label of the eigenfunction. And as we have told, the problem with this is non-normalizable. But physically, that's not a problem, right? What we said is like in real life, in nature, we don't see things like this. We see wave packets, right? Wave packets are packages of these functions with different p's, and they are normalizable. So from a physics point of view, there is no problem. There's like a mathematical problem, and we have to find a consistent way to deal with this mathematical problem. And the way we will deal with this is we are going to use Dirac, so-called Dirac normalization. So here's the identity we derived previously. So this is dx e to the I k minus k prime x is equal to 2 pi delta of k minus k prime. So if you remember the way we derive this, if you want, we regularized this integral by putting it in a box, right? But the box we put, if you remember, was not infinite box. We used a box with periodic boundary conditions. And after we derived all the equations, we let the size of the box go to infinity, and that limit produces this delta function in a consistent way. Now we are using that result. Then, if I define now f of p x with this kind of normalization, 2 pi h bar e to the I over h bar px, then it obeys this kind of normalization, right? And let's check. What we want is to find this dx from minus infinity to plus infinity, f of p x star, f of p prime of x, right? So that is the normalization we want to show. And we will use this Dirac identity. So this is, let me plug in 1 over 2 pi h bar. This is from minus infinity to plus infinity. This one is going to bring me minus, this one is going to bring me plus, and this is going to be e to the I over h bar p prime minus px dx. And then I use Dirac identity, so this is 1 over 2 pi h bar. So this is delta of p prime minus p over h bar, right? Because I also have h bar here. And we use this thing, delta of cx is equal to delta of x over c. Then this h bar is going to cancel, there is also, right? There's like this 2 pi, which I forgot. There's also 2 pi. And this thing gives us delta of p prime minus p. Therefore, what I say is, here is the way I define my orthonormality. I have these continuous functions, f of p prime, and they are delta of p prime minus p. Okay. So this is not the normalization, but this is not the orthonormality we had in the previous course, but this will be consistent and it will work. And what did we say? So eigenfunctions eigenvalues of a Hermitian operator are first real, corresponding eigenfunctions are orthonormal. That was the second thing we put. And lastly, they are complete. That means we can write any other function in terms of eigenfunctions of a Hermitian operator. So in this case, let's also try to do that. we say f of x can be written in terms of eigenfunctions of this Hermitian operator, but in the continuum case, right, this discrete sum should go to integral, and this is dx. I think this should be dp. I have a problem in my notes. So this is dp. This is c of p, some expansion coefficient, and this is fp of x. Right? And if I open this up, I have minus infinity to plus infinity dp over 2 pi h bar cp e to the I over h bar px. And this is the Fourier transform, right? And how do I find the expansion coefficient? The expansion coefficient is c of p, is basically whatever function I have here, like this, I take fp f, right? And that's it. Let me just write it like this. And this is, if you want, the inverse Fourier transform. So also an additional note on orthonormality. So previously we showed this, right? fi star of x, fi of y is equal to delta of x minus y. We call this one the completeness, and we can also check it for this problem. For this problem, it's going to be dp fp star of x. Now p labels are going to be the same, but argument of the function is going to be different. So this is fp y, right? And this is 1 over 2 pi h bar dp e to the I p. Now y comes with plus, x comes with minus, and there's 1 over h bar, and this is exactly the same Dirac identity, right? And this is immediately delta of x minus y as before. Now let's try to think about, so this was for momentum operator, right? Let's try to think about the position operator and see if we can come up with something like this. Consider position operator. So now I am going to put a head on x, and the values I expect are going to be from minus infinity to plus infinity. So we want to find eigenfunctions and eigenvalues of position operators. Suppose, like let's suppose a function f of x has eigenvalue, let me call it x naught. Under x operator, and what this means is like I need to have something like this: x as an operator acting on x should give me x naught f of x. Okay, but we are writing all of these in position space. We are going to see an alternative momentum space maybe in the next lecture. So this is, so in position space, x f of x, right, as an operator gives whatever x is, x f of x. Then we need to think about a weird equation like this. I mean, it is simple, but making sense of it is weird, at least for me. Operator x acting on f, so this is x f of x, and this should be equal to x naught f of x, right? Because that's the eigenvalue I am looking for. So this is position operator. So this x in position space x hat gives x, and this is the eigenvalue we are required to find. How do we find this? Like, what is the, right? If it was like a differential equation, I need to find a function x f of x should give me x naught f of x. Right? It's, at least for me, it's a little bit disorienting, right? Now we are not solving differential equations, and we have to, right, come up with something. And I think at least my strategy is substitute, right? Try a couple of things and see if it works or not. For example, let's try sine of x. X sine of x is equal to x naught sine of x, and it seems like it is giving me x is equal to x naught. It's like a little bit constrained equation, right? It is not exactly what I want. So this only works if x is equal to x naught, but I want something that works even when x is not equal to x naught. You can, I don't know, try anything else. X e to the minus alpha x is equal to x naught e to the minus alpha x. The same thing. It works only when x is equal to x naught. And I think the answer is, like, let's try delta of x minus x naught. At least that's what Griffiths is suggesting. And if you do this, x delta of x minus x naught is equal to x naught delta of x minus x naught. It's a little bit silly, in my opinion, to write it this way, but it works, right? It is consistent. If x is hitting on delta function, right? Delta function takes it and turns it to x naught. Like, right? So this works. And you can consider two different functions, right? f1 of x, let me call this delta of x minus x1, and f2 of x equal to delta of x minus x1, and x1 not equal to x2, I assume this, and I can check if orthonormality as we defined works. What was it? It is f1 f2 is equal to dx minus infinity to plus infinity delta of x1 x minus x1 delta of x minus x2, right? And this is delta of x1 minus x2. That also works. So this is, I mean, not in the sense previously defined in the lecture, but so it works in generalized Dirac normalization sense, or generalized Dirac orthonormality. Good. Any questions? You can also think about completeness, like let's check completeness. Any function f of x can be written in terms of these, right? Let me call it the x prime minus infinity to plus infinity, some expansion coefficient c x prime, and the functions I'm trying to expand, which is delta of x minus x prime. In that case, c of x turns out to be f of x, trivial. The expansion coefficient turns out to be the function itself. Good. How many people feel tired? I don't know, a little bit more to show, but if you don't feel like it, we can call it a day today. So we want to finish? Okay, let's call it a day and we can continue next time.